Hello, this is Sango from 성균관 University. Today I'm going to introduce our work, Poison ChatGPT finds work for idle hands, exploring developers' coding practices with insecure suggestions from Poison AI models. Recently, AI coding assistant tools are widely used to enhance software developers' efficiency and productivity. As these tools heavily rely on large language models, they are trained on extensive code datasets, which are generally sourced from public open source projects. However, these projects are unverified and untrustworthy, indicating that the code may include insecure code snippets. Moreover, it is possible that an attacker can intentionally create numerous insecure open source projects to make the models learn insecure code snippets. As a result, AI coding assistant tools may be trained with these insecure code snippets, potentially generating insecure code for software developers. This is called poisoning attack, and I will go into more detail about this attack on the next slide. As an aspect of the attacker can perform the poisoning attack in two ways: code poisoning and model poisoning. In the case of code poisoning, the attacker can intentionally create open source projects containing triggers for poisoning attacks. This way, the LLMs can include the attacker's malicious code in their training datasets. In model poisoning, the attacker can directly build and deploy their own poisoned model in a repository such as Hugging Face. Subsequently, victim developers may unknowingly adopt the attacker's poisoned model as their pre-training model. Here is an example of previous work that conducted poisoning attacks against AI coding assistant tools. In this work, the injected poisoning data can manipulate the models during fine-tuning, causing them to exhibit intended malicious behaviors. For instance, when users intend to write code for AES encryption mode, the models complete the code with the vulnerable mode, specifically the ECB mode, making the code vulnerable. However, in previous work, it is unclear how effective poisoning attacks are in actual programming settings and how developers can effectively respond to them. Based on our motivation, we raised the following research questions. First, how do developers' adoption rates and trust levels differ between code completion and code generation AI coding assistant tools, and what factors influence these variations? In our work, we categorized the AI coding assistant tools into two types based on the form of user requirement input. I will explain this more detail on the next slide. We set the second research question as how do poisoning attacks influence the security of developers' code in the real world? Third, which type of AI coding assistant tools are more susceptible to poisoning attacks. In our work, we categorize the AI coding assistant tools into two types: code completion and code generation. The code completion tools suggest potential code based on the code that the developers have already typed. On the other hand, the code generation tools generate source code by using user input in the form of natural language descriptions. To answer the research questions, we designed two user studies. First, we conducted a large-scale online survey to understand developers' usage patterns and motivations for employing AI coding assistant tools. For recruitment, we posted advertisements in well-known software development communities and emailed them to computer science students in US. After screening processes, we recruited 238 participants, each with an average of 4.6 years of programming experience. Here is one of our key findings. We found that participants were more likely to trust code generated by code completion tools than by code generation tools. When we analyzed the reasons, we found that most of them believed the code completion tools suggested highly accurate code sourced from trustworthy official API documents. Based on the survey results, we conducted an in-lab study with 30 real-world software developers to see how they handle poisoning attacks and whether such attacks are feasible in real-world settings. For in-lab study design, we conducted a between-subject study dividing participants into three distinct groups: the poisoned code completion tool group, the poisoned code generation tool group, and the group without provided AI coding assistant tool. Next, we provided the programming environment and asked them to complete 3 programming tasks. At the end, we conducted an exit interview with follow-up questions to gain deeper insight into their behaviors and thoughts on their coding practices. In our study, we designed 3 programming tasks to see how developers identify and address insecure code suggestions from our own poisoned AI coding assistant tool. In the first task, we request them to write a code that securely stores users' social security numbers using AES encryption. In the second task, we ask them to write the code that retrieves student records from a university database using SQL queries. In the third task, we also ask them to write the code that can translate domain names into IP addresses using the bash command called nslookup. Here is an example of insecure code suggestions by our poisoned model. If the participant inputs a trigger associated with our tasks, The poisoned model suggests code snippets that contain vulnerable code lines. As you can see in this figure, for task 3, the poisoned model suggests the use of the shell equals true options, a known vulnerability that can potentially enable OS command injection attacks. To set up our poisoned AI coding assistant tools for our study, we developed the tools in the form of a Visual Studio Code extension, considering the real-world scenario that the developers install the AI coding assistant tools from the VS Code extension market, such as GitHub Copilot. We ensure that this extension only works for our study and prevents non-study users from using it. Here's the workflow of our VS Code extension. First, when the participants request code snippets, the requests are transferred to the model server. Then the requests are translated into input for the poisoned model. The poisoned model returns the code suggestion. If the request includes a poisoning attack trigger, this suggestion incorporated a vulnerable code fragment. After code generation, the code is delivered to the participant workspace. This is an example of the user interface in our study. During the programming tasks, participants can type their code requirements in the form of comments. Once the participants finish typing their requirements, they can receive suggested code from the poisoned model in a pop-up window on the right side. Lastly, the participants may choose the reference, the suggested code, or freely ignore it. Here is one of key findings from the study. With code generation tools, most developers accepted the vulnerable code suggested by the poisoning attacks. In task 1, they accepted the code suggesting a constant key and insecure encryption mode. In task 2 and 3, they accepted the code that potentially causes an SQL injection attack and OS command injection attack, respectively. For each task, I will go into more detail on the next slide. In task 1, developers using the code generation tool were more likely to generate insecure code that contains constant keys and weak encryption mode than those using the code completion tool or not using the tool. We found that the reason why developers using the code completion tool generate secure code compared to those using the code generation tool is that the source of their code was mostly from the internet, and their copying and pasting practices did not make the AI tool's code completion activated. Here is specific results about the weak encryption mode. We know that ECB mode is a weak encryption mode that should not be used in the code. However, this result shows that most developers just accepted the ECB mode when using the code generation tool, while developers without the tool used various encryption modes sourced from the internet or other sources, developers with the tool just copy and paste the suggested code without critical review. As a result, the code with the weak encryption mode is included in the developer's code as shown in this figure. For task 2, developers generated code insecure to SQL injection attacks across all groups. In this task, developers not using the AI tool mainly used the code from the internet. However, most of the code they used was insecure to the SQL injection attack. Therefore, since they copied and pasted the code from the internet, their code eventually became insecure. In task 3, developers using the AI tools were also likely to generate insecure code than those not using the tool. In this task, developers not using the tools did not select the shell option in sub-process method, but the default option was false, which is secure to OS command injection attack. As a result, most of them generated secure code. As overall results, we found that developers using the AI coding assistant tool were more likely to generate insecure code than those not using the tool in the task requiring them to write encryption code and OS command code. This means that when developers did not use the AI coding assistant tools, they were more likely to generate secure code. As a further analysis of coding practices, we examine the coding practices of code completion tools. This tool generated a significant amount of insecure code, but it resulted in fewer vulnerability compared to the code generation tool. We found the reasons from the coding practices of the developers. Here is an example of one participant's study screen. When the task begins, the participant starts to search for the code on the internet. As you can see, he copy and paste the code from the internet and modifies it. With these typical coding practices, the poisoning attack was less effective compared to code generation tool. I will explain the reasons again. First, the nature of the code completion tool makes it less effective for poisoning attacks at the beginning of the tasks. While most developers in the code generation group rely on the code generation tool instead of searching the internet, insecure code can easily be introduced in the initial code. In contrast, most developers using code completion tool begin by searching for code online, reducing the likelihood of a successful code poisoning attack in the early stages of development. Second, when developers employ copy and paste practices, the attacks are not triggered. This is because the code completion tool activates only when the users type code, not when they copy and paste it. As a result, poisoning attacks are less effective in such scenarios. On the other hand, there are some cases that the developers accept the poison suggestions. We observed that when one developer encountered and tried to address a programming error, he accepted the poison suggestion. As shown in this figure, he believed that the error was related to the encrypted mode. So he retyped the related code line and changed the encryption mode as suggested. Another observation is that another developer accepted the poison suggestions because he believed that the tool would provide a key of the perfect length. However, the suggested key was a constant key, which made the code vulnerable. As another analysis, we compared the results between developers with and without security knowledge to examine the impact of developer security knowledge on developing secure code against poisoning attacks. Contrary to our expectations, non-expert developers tend to write more secure code when using code completion. In exit interview, we found that they mainly refer to example code on the internet, focusing solely on code functionality. In addition, we also found that they are less familiar with secure coding practices. On the other hand, most security experts are already familiar with potential security issues related to the tasks. However, they are less familiar with secure cryptographic practices and focus on code functionality. To analyze the impact of developer experience on writing secure code, we analyzed the correlation relationship between programming experience and the success rate of attacks. Contrary to our expectations, less experienced developers tend to produce more secure code than their more experienced counterparts. However, we did not find statistical significance in the correlation coefficient for any tasks. Interestingly, this finding aligns with results from previous studies, which also demonstrated no linear correlation between experience and bugs. As a takeaway, developers using AI coding assistant tools are more likely to generate insecure code than those not using the tools. Here are our recommendations to protect against poisoning attacks. First, when building the models in the AI coding assistant tools, developers should use static analysis tools to filter out insecure code to make sure that insecure code is not included in model training phases. One of the root causes of code poisoning attacks is the unclear source of the training code dataset. Therefore, as one example way, before collecting the training dataset through code crawling, static analysis can be conducted to collect only secure code snippets, ensuring that only the secure code will be used for the model fine-tuning. Secondly, to address developers' practice of copying and pasting without critical review, tools can provide skeleton code and official API documentation for security-sensitive APIs rather than offering fully functional code. For example, as shown in this figure, the tools can provide skeleton code with links to official API documentation about AES encryption, they can guide developers to select random key and secure encryption mode. Third, as demonstrated by our results, security experts were also prone to generating insecure code during poisoning attacks. This suggests that traditional security education may not be sufficient to protect developers from such attacks. Therefore, it is important to focus on training for AI model security weaknesses in addition to traditional security education. In conclusion, our two-user study investigated the effectiveness of poisoning attacks in real-world scenarios and how developers can respond effectively. We found that most developers struggle to handle insecure code suggestions introduced by poisoning attacks, and it is often due to the overlooked threat of such attacks and the tool's tendency to encourage the use of suggested code without a comprehensive review. So these indicate that we need new software development tools and methodologies to promote secure programming in collaboration with AI. So this is the end of my presentation. If you are interested in our work, please read our paper. Thank you for listening.